and hit share the screen. There, there. Okay. All right, so we're sharing. We're going to go to the VM. We're going to log in. Okay. It's going to be des. All right, so we're going to navigate to where we were with our CBC code, and I'm just going to copy that, create a new copy called des. So here we are on the VM. So we can go ahead and just take this. As you can see, with a lot of these scripts, they just build pretty much on what we did the week before. So it's kind of the same thing, just incrementally. That's what's so great about block ciphers. Right? It's like one big algorithm that we looked at gradually. So let's cd into desktop. There, -L. And we can go into fall 2025. ITS 50 there. /L. So we've done substitution cipher XOR first. I have a feeling that's where we were last, because I copied that from the XOR hash or the XOR first. So let's see. What? Nope, it's not here. Hash XOR. We did this, right? Did we went over CBC at least a little bit? That's the homework that's due tonight. Oh, really? Is it really? Okay. All right. Well then, let's go over that. So the last thing we looked at was hash XOR. We did, let's see. Oops. Okay. So we created blocks. Okay. So then this is the latest that we have them related to this, right? So XOR, the hash XOR. Okay. All right. So I'll start with this one and I'll build up the CBC then at the Feistel. Okay. So let's go ahead and do that. I will create a new copy though. Yeah. So I'm gonna take that hash XOR. That one definitely has to have the break into blocks. So CP hash XOR, and we're gonna call this des XOR, and we're just gonna build it up, okay? .py. Okay, so it should be good now. /L. All right, so let's try that des then. Let's go in it with nano. Let's see where we are and what's missing, and we can start adding those sections, okay? So we've got your random, we've got gen key with byte arrays, we've got an encrypt and a decrypt that does do the job. You just have to extend the encryption approach. There's the hash function, which we're not going to need here. So to avoid like confusion, I'm just going to delete this because that's for the other algorithm. We did do create blocks, so that's good. We have the create blocks function. Okay. And then I have a plain text message there. Plain text. So we plain text printed. The length is 8. Print the length of the whole plain text. Then we create the blocks and we can list the blocks. We generate the key, print the key. We don't need this one anymore. I mean, we don't need to do integrity right now. So we can delete that one. I'm going to delete hash value 2 as I don't need it. All of these, I guess, are from the previous algorithm. Okay. Right. So this is kind of where we are, right? So we're going to do then a CBC XOR algorithm, okay, with this approach. And we're also going to add the Feistel network to it. Okay. So essentially, if you've done the homework, you're kind of there, and we just need to add the Feistel network. All right. So just to remind you, so what is the trick with the Feistel network that we'll be doing in the code? So I'll go to the whiteboard just quickly and remind you, right? So everything is pretty straightforward. We take a block and and we XOR it with either with the IV or a key or something like that. But in the Feistel network, if you guys remember, we have the block comes in, we have to actually split it in half, right? And then we're just gonna produce another pair of blocks that we concatenate like this. So it's 32 bits, let's say, produces 32 bits. And this process, imagine it's like, like you can do it multiple times, and these are called rounds, right? But essentially, it's just this key idea. And we have this notion of, let's say, R and L, and 1, R2, L2. So essentially, what is it? Sorry. 1 is pretty easy. This one just becomes that one, right? So they're literally just flips. So in the code, if you think about it, if we have an R and an L that goes in, what comes out is just an L and an R, right? Because one of them just gets flipped. And then the other one has to be XORed, has to be modified. So that's where this one comes into the F function, and then that gets XORed, right? So we're going to simplify this operation by just taking that R1, let's say, and if you remember, there's a function that we talked about, but one of the things that we said about the function on Tuesday is that's where the key comes in, right? Do you remember that? So we're just going to, for simplicity, XOR with the key, and that comes out here, and it's going to get XORed with L1. Do you guys see that? So that's essentially that's it. That's like most of it, right? And then after that, we would have to put in the F function and the definition of it. But for now, our definition of the F function is just an XOR operation between the key and the block that comes in. Does that make sense? All right. So that's going to be the simplification of it. We're going to do not 16 rounds, probably because it might take a long time on your computer, 2 to 3 times. However, this should be a parameter, right, that we can play with. So that's going to be the overall idea. I'm going to go over the logic first of how it would work. And then later on, we can, the thing that's going to trip us up probably is like getting those bit arrays properly formatted for the operation that we're trying to do. But essentially, I will go over the logic first. Okay? So that's going to be the idea. Okay, so let's start. So that's essentially, I wanted to give you the chart. So now let's go back to the code. So that's what we want to do. So now I'm going to share the screen. Okay, and we're just going to see how we can modify this script to reflect all of these steps. All right, so we have from random, we have pickle, all right? So I guess I remember now, I wrote it on the board. So you need to import, oops, the pickle library. Import pickle. So that's going to be spelled C-K-L-E. All right. That's what allows us to save the actual list of byte arrays into a text file, which makes it a lot easier than having to do anything else. Although we could also convert it into a string and then switch it back. But yeah. So let's kind of take a look at that. We're going to generate key. This is key generation here. Should be the same. So we have a function gen key of specific length. It returns a byte array random length. So we've discussed this one already. Then we're going to have encrypt. These encrypts are just to do a XOR between two blocks. So we'll have to elaborate on them a little bit more. And we're going to have to include the Feistel network operation. So we'll take a look at that. We're going to encrypt and decipher the message. Break message should be, or create blocks. That should be good to go. And then we have our main. So let's start with the main. That kind of gives us an idea of the flow of this, the functions that we have to create, and we'll go from there. Okay, so for now, I'm just going to use this string, so I'm not going to read from the file just so that I have less code going on. But later on, that's something that's pretty easy to modify. It should be pretty easy. All right, so we read in my message. We printed, so that's good. We've defined that the length of the block is 8. So we've got that. And we printed. At that point, we create blocks, provide plain text and the length, and that provides a list of blocks. Okay, so that's pretty much the same thing. We are going to need now what? We've used a key in the past, but now we need an IV, the initialization vector for CBC, if you remember, right? So I'm going to go ahead and do that. Key generation happens here, so it makes sense to do that in the same place. So I'm going to do first key equal gen key length, and now I'm going to do IV, so initialization vector, which can be also, for convenience, gen key of length. Okay, so that's easy enough. And now we're going to proceed to encrypt our message. So I'm going to go ahead, we can print the key also, I guess, print key, print IV. And let's just run it to make sure actually that everything is working. So I'm going to do Control X, Y, enter. Clear there. And I'm going to Python 3. Right. So nothing broke. At this point, we are able to break the message into parts, and I have the 2 byte arrays, one for the key and one for the initialization vector, okay, that I can use. So, I have available. We can go back to the code now. And the next part is having the message and having the key and the initialization vector. We can go ahead and do the encryption or start the process. So we're going to create a variable called cipher list, and we're going to define a new function. Let's call it encrypt message, which will call any of the other encryption functions that we have. But I'm trying to make the code as modular as possible, so it's easier to understand. So I've got encrypt message. And if you guys see any errors or anything, please let me know. Okay, so now we encrypt message. First thing is, of course, list of blocks, right? So that's the thing that we're trying to encrypt. So list of blocks. There we are. We're going to provide the key. we're going to provide the initialization vector, and we're going to provide length. Okay, so that's going to be our function that we need to define. And once the message is encrypted, we're just going to print it. And then, of course, comes like the whole decryption process. Right, but let's just go with this part here. So print cipher list, just like that. All right, now, of course, we need to define encrypt message. So I'm going to go over here and just like right here somewhere. I'm going to add encrypt message. So define encrypt message. Okay. And this will have inside, I'm going to change the name of the variable because here, it's the scope is just local here. So I'm going to say block list. And I'm going to use key and then IV. And then let's call it len of blocks, just like that, right? So we're defining the function and we're just going to think of the logic here. 1, 2, 3, 4. All right, so we have to consider how to encrypt the message. So we're going to try to produce a list of ciphers. So list of ciphers, right? So that's every block wants to be encrypted. So we're going to proceed as follows. So we're going to take every block, right, and run it through a Feistel network in this example. Do you see that? So we could essentially just XOR it with the key and the previous one, and that's it. But we also need to do the Feistel network. So in your homework assignment, if you've done it, you probably did encrypt 1 and you encrypt it with like the key, let's say, and encrypt 2 and encrypt it with either the IV or the previous block. That's essentially so I'm doing the same approach, but just keep in mind, I may need to tweak encrypt 1 or encrypt 2 to include the Feistel network idea. And that's just before that XOR, flip them, do the thingy, and then that's it. You see, it's actually like it sounds very complex in the lecture, but not so much, right? All right, so let's take a look at this. So for I in range, and this is going to be just the length of the list of blocks, because remember, I'm just iterating through each one of these blocks in the list. So I'm going to say len block list. Okay, that should be good. Colon here. 1, 2, 3, 4. 1, 2, 3, 4. So remember here, we're just grabbing each block, okay, by index, for instance. So the first step would be to do that first encryption. So let's call it cipher 1. Here we can use one of our built-in functions or one that we modify, right? So we'll see that in a second, but let's just take encrypt for now. And so for just the plain CBC, this is where you would just encrypt, let's say, with the IV. So I'm going to do IV here, which I have, and I'm going to encrypt that with what? The first index of block list, right? The first index of block list. So that's block list I. Do you guys agree with this? Right? So that's how I would get that first block. Okay. And there we are. Then so imagine what happened is I just took a block, XORed them, produced a new block. Now that one is called cipher 1, and it's going to be used in the next step to XOR it with the key, right? So we need to XOR it with the key. So I'm going to do cipher 2, and this one is going to be encrypt 2. And actually, in the CBC homework, encrypt1 and encrypt2, those two functions are actually the same thing. If you have to modify them, it's probably because of a byte array issue, like a formatting issue. But otherwise, because one comes in as text, right? One is coming in, the first input comes in as text, so you have to modify that. But essentially, it's the same operation. Okay? So here we'll decide where we do the Feistel network. You could do it twice. I mean, it's up to you guys, right? So that's the beauty of this, because it's a block goes in and a block goes out. In a lot of these complex algorithms, also in machine learning, it's kind of the same thing. Like a block comes in, some stuff happens, and a block comes out that's exactly the same, so that then it can go to the next step in kind of the same way. All right, so you're just transforming it a little. So here we have encrypt2, and encrypt2 takes cipher1, right? If you guys agree. So it'll take cipher1, just align these a little bit better. Okay, and the next one is going to be obviously the key. See that? So we need, of course, to define those cipher1 and cipher2, but by taking this approach, this code is great. Like we don't have, a lot of the logic is fine here, and we can drill down into the individual ones if we have a formatting error. So now that this is done, the block has been, produced. It's still n bits. N bits went in, n bits come out. Now I'm going to do list of ciphers, right? List of ciphers, which is this one here. And I'm just going to append this, add it to the list. Append. And what do I append here? The final block that has resulted, which in this case is cipher 2, right? That's the modified. Now, after I'm done with the whole process, I just go ahead and return what? List of ciphers, right? That's it. But there's an issue here. Let's go back to the whiteboard, right, for this one. So in just CBC, here we took an IV, right? That's what we just did. Took an IV, we took a block 1. They came in together, they were XORed, correct? That produced something, let's call it temp, or well, actually, no, it had a name, right? Cipher1. So it was called cipher1 in the code, right? And then what did we do? We brought in the key, XOR again, and that produced C1. Let's call it cipher1, right? The final one, the final output, the thing that got added to, and we added it to the list, actually. So this is the list, and this was added in there. Yeah? But now comes in the next block, B2. We need to XOR it with something to produce cipher1 again for that particular case. But what do we use? So in the previous one, we just XORed it with IV. Do we XOR it with IV again? Yeah, go ahead. Right. So then what do we need to do? We just this needs to go there, correct? So in the code, the equivalent way of doing that is just to make IV become C1. Do you guys see that? Is that clear for everyone? That's the trick. This whole arrow that goes like that is just that, essentially that idea. So let's translate that into the code part over here. I'm going to share my screen. Okay. So I just go, where am I? Just go here, somewhere here, right? and I need to change the value of IV. It can't be the original IV, but if you notice here in the code, right, we're going to XOR it with IV every time. So we just need to change that value to become, in this case, which one? Cipher 2, actually. Right? Cipher 2. The final encrypted byte array. Got it, guys? So that was the tricky part with the CBC algorithm, right? Just this is essentially CBC at this point, right? And then I just need to do CBC in reverse. And that's going to be when we do the decrypt part. But yeah, that's actually the hold encrypt message. Now, what we need to do is obviously we need to define encrypt 1 and encrypt 2. But before I move on to that, are there any questions on any of this logic? Yes, please, go ahead.
Couldn't you, like, this particular say, couldn't you change cipher 1 to just be IV and then get rid of the IV cipher 2?
Where?
Like,
Couldn't I?
In cipher 1 equals encrypt 1, you could change cipher 1
In cipher 1.
The encrypt 2 use IV and then IV.
Oh, so you're saying
IV equals encrypt 1 block left.
I think your question relates to me not putting IV here and just putting cipher 2 in here. So you want me to change IV? Let's do what you want to do. So here?
Yeah.
Uh-huh. And what do I change it with? The whole line.
Yeah.
Okay. Make this the IV.
And now you change the
But then I have to make this one IV, correct?
Yeah.
Okay. And yeah, I see what you're saying. So then in the future, you're going to be using this, not this one. The only difference is you didn't use the key for the previous element. And using the key would add a little bit more randomness, if that makes sense. It is used for cipher 2, but in the next, yeah, I mean, it is still used for every block. I'm just saying by using cipher 2 in the here for where we were renaming IV, you were adding more randomness, I would think, because we were using cipher 2 instead of the top one. The top one only used, but I guess, yeah, you're right. Both of them are kind of generated randomly. It's just that really the one that you keep secret is the key, not necessarily the IV. Yeah. I would think this approach, like what I said, because this one uses the key, so then that randomness is being added to the previous thing also. All right, so let's add it back. So I'm gonna do this stays like that. This should be cipher 1. Cipher 1. This should be cipher 1 here. Okay. And then we need to do the IV equal cipher 2. Okay. All right. So that's the encrypt message approach. Now let's take a look at, let's start defining encrypt 1 and encrypt 2. So I'll start with encrypt 1. Remember that just at this point takes a block, and it takes, the block, the plain text block, which is a key feature to know about, and it takes the IV, right? And so we want to define that. So we do have the encrypt functions, like this one, and I'm going to keep them, and instead just here add a function called encrypt1. So I'm going to define encrypt1 So define encrypt one there. 1, 2, 3, 4. Return. And this takes in, 2 blocks, right? So we're going to take a look at that. So let's say, yeah, plain block will be just some block. Plain block. Now in our encrypt function up here, we had the exact same thing, right? So a plain block came in, which was letters. So we had to do this process of converting the letters, and then we would XOR it with the key, which in this case would be the IV. Okay? So let's actually just do that. So that would be, so byte array. So I'm looking at this function here. So byte array, and then list ORD plain block I XORed with the IV in this case, I, and the range for I in range. So we can just use this encrypt here as the first step. Let me also, so since this is not the key, let's just use the IV. It'll just remind us that it's essentially that term. Okay? So then I'm going to go over here. 1, 2, 3, 4. This will produce block, let's call it. And I can just simply reference my encrypt function that's above. I'm going to do encrypt. And this is going to take plain block. Actually, I'm going to call this one temp block. Temp block. And this is going to be plain block. And is going to use the IV. Should be the same. Format as the key. Okay. So now let's take a look at what this produces. So I think the code until here should be good. So I'm going to do print temp block. And I'm also going to add an input here just to halt the program at this point. Okay. So let's see what happens. So let's see if we get the block. Control X, Y, enter. Python 3. Okay, perfect. So here we are. So far, we have been able to create a key. Well, we broke the sentence into blocks. We created a key, an IV, and we just XORed them and printed them, right? So, and we're reusing all the functions that we had, and I'm trying to make this as modular as possible. And you can see it's just a bunch of XORs all over the place. Okay? So now, I mean, if you guys have questions, please ask. But yeah, we just used encrypt to produce a temp block. So now this is where the Feistel network logic starts to sort of appear, right? So maybe to keep some of the logic simpler, I'm going to create a Feistel network function or a Feistel round. That's also handy if you're doing 16 rounds or 3 rounds or 5 rounds to have some of that code that's reusable. Do you guys see what I'm saying? So, but essentially it's what I explained. Remember, we just, this block, temp block, right, is what now at this point in time, if we go back to the whiteboard, yeah, so temp block is this one. We just got that temp block from the code, and that's temp block, essentially. So we are about to run it through the Feistel network, and then what comes out, it's kind of like temp block was, but it has been more jumbled and all that, scrambled, as they say. That's it. That's like essentially the whole encryption. I'm the only thing, remember, I'm kind of simplifying is this F function, those S boxes, and we discussed that on Tuesday, right? So the zeros and how we went from 6 to 4. So those tables would take a while to create, or I would need a library. So I'm going to skip that for now, but you guys get the idea. And that's actually a really important part of the security. All right, so now, yeah, so we are here, and so now I need to implement the code for the Feistel network. So let's go ahead and think about that one a little bit. Oops, sorry, I didn't mean to do that. This one. Okay, perfect. So we are back at encrypt 1. I halted the program, so we don't need to halt it anymore. Just gonna go ahead and remove this one. I'm going to comment this out. And now I just proceed to my process. So I'm even going to add some lines here just to indicate that this is more like the Feistel network logic. So this is essentially where CBC starts to become DES, right? The data encryption standard. Okay, so I'm going to go over here. And now we're going to take a look at this. So I have a block of 8. Okay, let's see how we need to split this, right? So that was the logic. If you remember, I need to split this into parts. So let's see how I can do that. So this is a byte array. So like a buffer. Okay, so let's try L. Just to remember those L and R things, right? So I'm gonna try to do that. I'm gonna take my temp block, and I'm just gonna try to like scrape or slice, I should say. I'm gonna slice the first 4 from it. Remember, what's the size of block? 8, right? So there's, 4 is the first half, and the other one should be the other 4. So I'm gonna do also R for my 2 blocks. Same thing, temp block. Oh, and this of course this needs to change. So if you've never seen this, what is the meaning of this? If this is a range of the buffer, right? So if I don't specify anything here, it means from the beginning. And then until 4, right out of the 8. So here, if I want to do the second part, I can do the same. So if I don't specify this, just goes to the end. But then I just need to indicate the starting position. So you might think 4 or 5, best way to figure it out is doing something like this and printing out the length. Does this make sense, guys, what I'm doing here? Just slicing it and splitting that block into 2, left and right. All right. So now let's go ahead and print these shapes just to see. So len of L and print also len of R. They should be equal to 4. And I want to make sure I'm doing all of these correct because the formatting can complicate things for us. All right, so let's try it. And let's add a halt here. Well, actually, we don't need it, I think. Let's let it. All right, so I'm going to try it again. Okay, so encrypt choose. Oh yeah, I do need the input, sorry, because I have that encrypt too. So let's add the input here. right? So we haven't defined encrypt2, even though I have a feeling that's going to be pretty easy. Control X, Y, clear. What do you guys think? Did it work? It worked, right? So I'm able to split my block into two blocks, 4 and 4. So now one just becomes the other one, like literally, right? And then the other one needs a few XOR operations. Pretty interesting, right? So let's go ahead and try that one. So I need to, I'm going to get rid of these because I definitely don't want that going on here. Okay. All right. So now what do we need to do? We need now the part of the rounds, right? So we're going to do, think about it. We have, first round, right? So the two blocks, they get broken up. First round, one goes down, the other one gets processed, it becomes this. That's round one. Then this becomes the input to the same process, right? So then this one goes down, the other one gets processed, and that's a second round. So we just need to repeat that process over and over for the blocks. Okay, so we're going to need some kind of a for loop here. So we're going to say for, we don't need to keep track of this. So when you don't want to keep track of an index, you can just say, um, for underscore. And then you just ignore it. In range. And we're just going to do 3 rounds. But in the example, I think it was 16 rounds. Just repeating the same shifting of the block. Shift the block, shift the block, shift the block over and over. Do you guys see the logic now? It's just like scramble it, scramble it, scramble it, scramble it. And we just have to be able to do that in reverse. As long as we can do that in reverse, it works. All right, so we do this. I'll add a comment here that this just means 3 Feistel rounds. Could be 16. Okay. Let's keep going. 1, 2, 3, 4. 1, 2, 3. All right. So now that we have this, what would be the next part? So we have L and R. So let's just rename it as L0 and R0. Yeah, like that. So we're gonna essentially take L. I haven't flipped them yet. So it's gonna be L and R, right? So yeah, L and R. So I want to do something here. I'm going to print these again. So I'm going to do print of L0, and I want to print R0. Here I'm doing all these prints because we have to be very careful here, right? The logic is actually quite simple, but the formatting of this can get corrupted at some point. So I'm trying to maintain that so that it all works out. So I have L0 and R0, and I'm going to put an input here. Okay, I'm going to put an input just to halt it again. Oops. All right. All right. So Control X, Y, enter. Okay. So I'm going to try this again. I had removed, I think, the other 2 prints. Yeah, so this should be my block split up. See, it's doing the 3 rounds. and it's a byte array like that. Okay, so now let's go back to the code. I could also potentially try to select something from L, such as this. So notice that in this one, I'm selecting something, and in R, I'm not, just to see the contrast, okay? That's all I'm doing. So let's do clear. $73. So it gave me, yeah, so that 73 is the interpretation of that byte array. Because remember that data is stored as byte arrays in memory. So if you notice what I'm saying here is only the data remain here. Do you see that? Only it's like if only this part remained by doing that. And I removed, so I took out the byte array part. Okay? So these are just when you're dealing with at this level in the hardware, you have to kind of think about that. So I'll choose which one we use. So for now, I just wanted to point that out. Okay, I'll leave the code in there just in case we have some issues. But I'm going to currently, so what I'm saying is I'll do this. Oops. I'll do that. And this just in case. But let's go with the full byte array. So L0 just equals L, and R0 just equals R. Okay. And I'm going to delete these for now. Don't need to print or the input. All right, I haven't done anything regarding the algorithm. I was mainly worried about conversion things and formatting. All right, so now I would send these into the Feistel network to do some processing. And the Feistel network will flip them and send them back. So I'm going to create a function for just one, for each round, it's going to be one function. Okay, so I'm going to say, for instance, here, we're going to call it rnew, comma, lnew. So this is like two blocks go in, one goes down, the other one gets transformed, and that's what lnew and rnew are. So what's coming out. So rnew and lnew, okay, equal. And then I'm going to define a new function, Feistel, and just to have a little bit more simplicity. So Feistel round. This is just one round. And it's going to take in as input L0, comma, R0, right? L0, R0. Do you guys see that? And notice, oh yeah, what I want to say, notice that the order matters here to help you out. So L and R go in, R and L come out. Do you see that? So keep that in mind so you don't get confused of the process. Here, as you remember, if we go back to the Feistel network diagram, this is what we're doing, and notice that there's an f function in there, and we've defined an f function to just be, the f function already took the key, right? So we're just going to define it as being, oh, sorry, this should be XOR. We're just going to define it as being an XOR operation between the block that is in there and the key. That's it. Okay, nothing else. For now, I could add the S boxes that we talked about, but that's just going to add more complexity. So to keep it simple for now, all I'm doing is XORing a block. So XORing R1 essentially with some key to produce another block that then gets XORed with L1 to produce R2. Okay, so that's the more complex part of this logic. So let's go ahead and go back to the code, because if we get through this, then we're good to go. Now in this part, okay, we have to think. So what is encrypt 1 doing? So encrypt 1 is this one, right? And it actually uses the IV, not the key, right? So that means that maybe we have to do encrypt 2 also with a Feistel network to be more secure and have the key in there. Do you guys see that? But essentially, as far as the logic is concerned, is the same thing. Okay, so we can just repeat it. So let's go ahead and work with IV. So obviously IV will need to be passed into the block. So IV needs to go in here. And IV was a byte array. So we also have the issue that IV is probably of size 8. These blocks are of size 4. So we need to think about how we're going to deal with that problem. Okay, so that's the other issue. So we can pass IV as the byte array here. All right, and we'll define Feistel round, but let's finish this logic because that might be easier. But really, that's it, right? So once I have this, our new would just become L again, right? So they would just become, so L new would become L. L new would become L. Why do we do this? Because we're going to do 3 rounds, remember? And so whatever we produce here has to go into the next round, right? And then whatever we produce after this Feistel round needs to go into the next round, and so on. So we have to do that. So that's why I'm assigning it like this. Obviously, the code could have been shorter, more efficient. I'm being very explicit so that everything is clear, right? Let's do the other one, R. And that's going to be our new. Our new, and these should be byte arrays, by the way. And then once we have these 2, these are still blocks of 4. So we need to, yeah, so we do the 4 rounds, we're done. And then what happens after we're done with the 4 rounds? What's the last step? We have to take those 2 blocks and do what with them? Those 2 blocks of 4 needs to become a block of 8 and come out, because we're done with the Feistel network and we're back to our normal processing. Okay, so that means here 1, 2, 3, 4. We need to, the return. Sorry, actually, I had the return down here. So I just have to go to return here, and I'm going to say L concatenate somehow R. And for byte arrays, this should work and concatenate the 2. If not, again, we'll have to issue some kind of formatting. But that's it. We're done. Do you see that? That's essentially the whole Feistel network in forward motion. Okay? Some problems with formatting, etc. That should be good. So assuming here, by doing this, we have that block of size 8 that went in, we split it, we did the rounds, did 3 rounds, then the 2 blocks become 1 block again of 8, comes out. Done. So now we go back to our code. Encrypt 1 should return a block of 8. That's, encrypt 1. That's really great. And then that goes into encrypt 2. If this is a byte array, right, then we can look at our function encrypt here. Okay, so this one was for just plain Okay, so now we need to have a function encrypt2. Yeah, so let's do encrypt2. So we did encrypt1, which calls encrypt. Yeah, here's encrypt, right? Now we look at cipher2 and cipher. So this one encrypt2. So let's define that one as well. And then we'll test all of this. And go. This one should be a lot easier. And I'm just for the sake of simplicity, I'm not going to add the Feistel network here, but you could also add it here. And that actually would be the more secure approach. We can later, if you guys want, do that. Okay. So right now, I just want to make sure all this works. So encrypt2 is that second step. That one assumes not a plain block, right? This would be a byte array block, right? You guys agree that at this point it's so let's call it a temp cipher block, something like that. Remember, this is of size 8. This one takes in the key itself, if you remember. So this one has the key itself, colon, 1, 2, 3, 4. And this one just returns a byte array. It's a lot like the other one. Byte array, open parentheses, close parentheses. And then this is a list comprehension for I in range. I'm using the same logic. Now this, we need to define the length. So length of temp cipher block. Temp cipher block, like that. And of course, here is where we XOR the elements. So here we need to take temp cipher block, and that's by index. So we grab the index first, right? And we just use the caret symbol. That is our XORing operation, and we XOR it with the key. If they are both byte arrays, this should work just fine. Do you guys understand? And that's it. So the only thing I should have done probably is encrypt2 should have had the Feistel network, right? Instead of encrypt1, but let's go with this for now. And as I said, we can modify it. Any questions? That's kind of the whole logic of this whole Feistel network minus the S boxes. But let's try it out. So now we should try it out. I'm gonna put a halt. Oh, sorry. I actually haven't defined the Feistel round, right? So we need to define this Feistel round before we run it. So Feistel round. We have to think about what goes on in that Feistel round. So let's do here. Um, like that. Define Feistel round. Feistel round. Take some parameters. 1, 2, 3, 4. Return. All right. So what parameters does it take? So it takes L0 and R0. L0, R0, and the IV. Okay? Lowercase IV. So it takes these 3 parameters. So we have to think of the logic, right? The 2 blocks come in. This is where the left block just becomes the right block, right? And then this other one, we need to do some steps. So let me do. So R just becomes let me think. Let me like write it on the whiteboard. Okay. So that this is clear. Because this we're flipping and we're doing things. It might be a bit confusing. All right. So we got our Feistel network here. We've got the function f. It's got L, R, and let's say the IV. Okay. So we define colon. We know that we're going to return something, right? So, and let's, the blocks, right? Like that. So this should be this L and R, 1 and 1, and this is L2, R2. Okay? So then L this one goes like that. So we need to have R just becomes L, right? Do you guys agree? So that, yeah. And now we need to do L that goes over there, right? So that one needs to XOR with R. Okay, so that would be caret R. Okay, we got that part. And L goes into the F function. Remember, so there's an F function here. And we're saying that for now, all we're doing is XORing with the key. So this F operation is just going to be L XOR key, right? And what comes out of that goes in to be XORed with R. So then this would be L caret key. What do you guys think? Do you agree? So that's essentially the operation. So we can do, yeah, so we XOR foreign key. Okay, so that's it. Okay, so then we can, let's see, so we can do a variable f out, like a temp variable. This is the equivalent also of R XOR key. We can do that too, right? It's the same. I take these two values and XOR them, it's gonna be the same. So XOR key, and then L now simplifies to just L XOR F out. So we can then delete this. What do you guys think? All right. So this is the approach. This is the hard part, right? That we have to and that kind of makes sense to be separated out. Okay. So there's these XORs. These are byte arrays of a specific size. We have to look at that. And we still have one problem. The key is of size 8 in this situation. So what are we going to do about that? Okay. So let's go ahead and, because remember, in the example that I gave you on Tuesday, we expanded the size, right, of the block to match. And we were doing a few other things. So in this case, and also we were doing like 32, this is 8. So we have to, it's a little bit different in that regard. So let's go ahead now and try to define this one. Okay, so we know L0 and R0 are of size 4. They should be byte arrays. But this one is of size 8, and it should also be a byte array. Okay, so we just have to figure this out. So here, I'm going to create F out. And this is going to be the first place where I might have a problem because I have R 0. And I need to XOR it. With the IV. So, which would be that. But it's not going to work because of the dimensions. Okay. Let me try something here. So I'm going to do R0, L0 here to produce F out. I'm going to say print F out. I'm going to halt the program also, input. So I'm halting it. And I'm going to just write a message here. Print F out. All right, so let's try this. Let's see. Let's not keep adding more code as it can break. Let's see where we are. Okay, but okay, so yeah, so this operation byte array is not supported, so we have to use the actual functions that we've been defining. So we have to see if we can repurpose one of the functions. So for instance, encrypt, let's see, encrypt. Encrypt works for plain text. I think we're going to have to write it out, unfortunately. Encrypt2 actually takes a block and another block and just encrypts it, right? So maybe this one will work. So let's try encrypt2 just to do that opera. Otherwise, I'll have to define a full generic function for this. Encrypt2, I think that's how it's written. Yeah, encrypt2 takes 2 blocks that should be byte arrays. In this case, L0 and R0, the size should not matter. Okay. And produces a result. So let's see if this works. So it seems like it actually did work, right? So that's good. That's good news. So if that worked, we're just dealing with one problem, and that's the key size, right? So I need to, we need to decide what we're going to do. One simple solution is just use half of the key for this one so that we don't have to, because otherwise we have to add a whole bunch of lines of code to expand it, but you guys get the idea. And just be consistent that we're always just using that first part, and that hopefully should work. So let's try that. So what I'm going to do here is first I'm going to try it with just the IV. This should not, because there's a size mismatch, but let's see. So IV, right already, okay. That's interesting. All right, so let's take a look. I'm using encrypt2 L0. This should be, let's change this to R0. And I'm going to use IV4. Okay, let's try that. What's possible is that it did, this comes from, it probably didn't, it only XORed 4 and not the other 4, so it left them in plain text. So if you think about it, the function that I'm using could have done that. All right, so let's try this approach here. So if you notice, I'm just using the first 4, I think. We should probably print the shape. Yeah. So this looks better, right? So this looks like a little bit better, but I just used half of it. So it's just for the dimensions. Okay. So yeah, so I think actually we should be good. So um I'm going to print this shape actually just to double check. This is going to be len of IV4 close parentheses, close parentheses. So let's take a look. Oops. And object has no. How did I do this before? Probably that. Okay. Yeah, there it is. Okay, perfect. So it is size 4. So that's good. Okay, so now everything should be aligning. Everything should be good. So let's do clear here. And I think we're almost then to the point where we can finish this up. So we have, we XOR R0 with the IV, but only half of it. Okay, we're all just consistently going to use this first half, and that should work in reverse, hopefully. Okay, and then F out then is going to become L. So it's going to be L, which will be L0, L0, F out. Okay, so now we need to rewrite this, of course, as L equal encrypt2 of L0, which is a byte array, with F out. Now, F out should be 4, so then we should be good for that one. So F out like that. Okay. And then we can comment this one out. That. Okay. And now we have L. Now it has been processed. So we just return these. So we return L, L, and we return R0. because R0 becomes, yeah, the new L. It's the order. This little order is what's, yeah, right? So think about it, right? So that's like it trips you up, right? So L becomes R, and this one with this one becomes L. Yeah. So the thing with all the complexity becomes L, and then this one just becomes, it's like they're inverted. It's like that. Okay. So now let's go ahead and run this. I'm going to remove all those prints. All the logic should be there now. So the Feistel network function, Feistel network round should be done. See, these come out here. We concatenate them and encrypt one. And so now we want to make sure that encrypt one works. So we want to print cipher 1. Okay. And make sure that we are getting a block. So print cipher 1. I'm going to put an input here just to halt it. And we want to also look at the length, which should be equal to 8. And that's the key thing. Okay, so I'm going to do print len of cipher 1 like that. Do you guys see that? So this is key here, right? To make sure that I produce the result. So let's try it. Whoops. It worked. Do you guys agree? We got a byte array and is of size 8. Any questions? Yeah, of course. But you can see how that's confusing, right? The Feistel network in my head, I'm getting it mixed up, and that's kind of the point of it, right? And it scrambles your data, and it worked for many years. Yeah, so they're all coming out as 8, right? Perfect. So yeah, so I'll go back to the code, but a couple of like good news, right? So one good news is even if let's say that it seems like the hardest part is this one, right? This Feistel little round jumbles you up a little. Even if I got the logic wrong a little bit, we can always tweak it. But what was great is the formatting is not breaking, right? We can XOR byte array with byte array, and that's really key. And then we can play with this. Obviously, we will know if we made a mistake when we decrypt and it doesn't decrypt to the correct thing. Do you guys see that? But that's it. So we are actually, I believe we're done with the Feistel network. I should have probably done it in Encrypt 2 and instead of, sorry? Oh, do you have a?
Yeah.
You want to see Encrypt 2? Yeah. This one, it's right there. As I was saying, I probably should have done this in Encrypt 2. Now that I think about it, to have more security, because the key is actually being passed. The other alternative would be to move the IV down and move the key up. So that might be a simpler solution that makes everything work. Do you guys see that? So we can think about that a little bit. But anyway, this should do the whole encryption, I think. Any questions? Now we just have to do that whole process in reverse, right? And decrypt. But I think you guys, even on your own, even though I'm not assigning this as homework, you could play with this one and probably, because you have all the elements. Now it just needs to be reversed. But I mean, if we have some time left today, so I'll try to get as far as I can. And then if not, we'll continue it on Thursday next week. But we're close. You can see how these algorithms are not really that complex to implement. But this essentially is like very close to an actual symmetric encryption. All right, so let's keep going. All right, so let's take a look. Let's see where we are. So we went over this. We got pickle in there. We can use it. We can generate key. Got some functions like encrypt. I should have used better names probably because some of them I reused quite a bit. But essentially, whenever I need to XOR two blocks of any size, some of these are very useful. Or if I have a plain text and a byte array. The Feistel round, as you saw, break the block, encrypt the two blocks. Had to do a trick here because to simplify the code. So just used half of the key. So we just have to make sure we're always using, possibly that first half as order would be maintained. Should work. And then we encrypt the F out with the other term L0, and then we just return them. So I got encrypt 1, which does the rounds. And then the Feistel network here is invoked, the Feistel network function. Encrypt 2 is just a simple encryption with the key. I have not defined decrypt, but this is encrypt message. So so I can get rid of this now, I believe. I don't need these two print statements. Ooh. Okay. And then create blocks was done. And then list of blocks, and we print list of blocks. So really here, right? So we want to get, I'm gonna do print done here just to make sure that we can get here. But we should print a list of cipher blocks if everything worked out correctly. So I'm gonna do clear. Done. Okay, so there we are. So we've applied des in forward motion and created a list of byte arrays, of cipher blocks. So this is now what you could encrypt. So this is your movie, your Netflix movie, totally encrypted, done. Okay. Now we have to repeat the process in reverse. Okay. So we can do that now, or we can save that for next Thursday. It is 5:30. So what do you guys want to do? Save it? And you guys will work on it also and try to solve it on your own. It's actually a nice exercise because this is actually CBC, which was the homework, right? And you've got the forward, so now try to get the reverse. Think through that logic in the Feistel network in case I, try to redo it again just to double check. But yeah, all right. I will post this code since I did make some it's already on on GitHub, but I did make some modifications to it, so I will post this one probably as des XOR 2. Okay, and you'll have it up there. All right. Don't forget, please, and I'll end the video.